1. Seal assembly failure inside the polished bore receptacle, PBR. This illustration will show the seal assembly partially landed or worn. Inside the PBR, the seals are designed to provide a primary tubing to annulus isolation barrier. When the seal OD does not match, the PBR ID or the seal stack becomes eroded by high production velocity, scale, or solids. Microannular flow begins. As the condition worsens, communication between tubing and casing becomes continuous, resulting in a barrier breach. This failure is often progressive and may not show high surface pressure immediately, making early detection difficult in high-rate wells. 2. Polished bore damage/scoring. The polished ID of the PBR must remain mirror smooth to engage the seal assembly elastomers correctly. When metal-to-metal contact occurs during fast RIH, or if debris is dragged inside, the PBR becomes scratched, pitted, or scored. Even a few microns of surface damage can prevent full sealing contact. The result is incomplete seal engagement, which allows annular flow or slow migration. In sour service wells, corrosion pitting accelerates the damage, eventually causing long-term barrier failure and possible tubing collapse due to trapped annulus pressure. 3. Seal assembly unseating during pressure or temperature change. Permanent seal bore packers rely on the tubing length, seal stack compression, and packer setting depth to keep the seal assembly in place. When well temperature increases from gas production, ESP heat, or injection cycles, tubing expands upward, reducing seal contact force. When temperature drops, tubing contracts downward, causing partial unseating. This thermal cycling effect can create intermittent seal loss, leading to crossflow or annular pressure buildup. The illustration must show tubing movement relative to the PBR. 4. Packer element degradation over time. Permanent packers use elastomeric sealing elements designed for long-term isolation. In HPHT wells, these elastomers degrade due to thermal cycling, chemical incompatibility, H2S, CO2, stimulation acids, and long-term creep. As the elastomers lose elasticity, they no longer maintain radial contact against the casing. The packer may still appear set, but isolation is compromised. This degradation is one of the most common causes of annulus communication in old wells, especially if the packer was installed for greater than 10 years. 5. ESP vibration leading to fatigue at the seal area. When an ESP system is installed above a PSBP, long-term vibration transfers down the tubing string. This cyclic energy causes micromovement of the seal assembly inside the PBR. Over time, this results in elastomer fatigue cracking, metal wear, and permanent loss of sealing integrity. The illustration should show vibration waves traveling down the tubing to the seal stack. This hazard is more pronounced in high-rate wells with deep ESPs. 6. Inability to retrieve or mill due to hard cement/scale above packer. Permanent packers are designed to stay in place, but when scale, cement, or debris accumulates above the packer, it becomes impossible to latch into the seal bore or pull the tubing. During workover, the operator may attempt milling, which poses risks such as swarf circulation problems, casing damage, and BHA vibration. The illustration should show cement/scale buildup acting as a plug above the packer and blocking access. 7. Cross-flow between reservoir zones. In multi-zone wells, dual string, commingled, or smart wells, a PSBP isolates zones with different pressures. When the polished bore seal fails, a high-pressure reservoir pushes fluids to a lower-pressure zone, creating cross-flow. This can damage both reservoirs and may lead to well control issues at surface. The illustration must show arrows indicating flow from HP to LP zones across a failed seal. 8. Loss of tieback seal in multi-string wells. Tieback seal assemblies rely on compression and precise landing depth inside the PSBP. Any debris, incorrect landing, or thermal movement causes unseating. This results in tubing losing its mechanical and hydraulic barrier. Annular pressure increases, potentially activating the SSSV or shutting in the well. The illustration should show a tieback seal, slightly lifted or uncompressed, inside the PBR. 9. Incorrect running procedure. Correct PSBP installation requires controlled run in hole, correct tubing spacing out, and confirmation of seal engagement. If the running BHA is misspaced, or the tubing is not properly picked up to compress the seal stack, the packer may appear set but not fully engaged. This leads to instant barrier failure once the well is put on production. The illustration should show tubing not fully landed or misaligned relative to the packer and PBR.